Hello. So my last video was on this exact topic, but it turned out that during the editing I saw that I was a little bit too shaky in the video. So I will re-record this. We're gonna do the Gaussian integral using the more usual method. This method originally was by Poisson. This is the usual method you see this being done, by the way. It's transforming the polar coordinates. So we start the same way. We notice the function is an even function, and we square by integrating in 2 dimensions. So originally we have the Gaussian integral, the exponential of minus x squared dx from minus infinity to infinity. And to square this, we're gonna integrate from minus infinite to plus infinite in x and y of the exponential of minus x of e to minus x squared plus y squared. And there is a big difference here. We're gonna do things in the polar coordinates. So let's do a bunch of stuff now. Okay, let's go to polar coordinates. So this I squared, the integral that we want to square, suggests us that we should use a distance in our coordinate transformation, and this distance is gonna be r squared, which is x squared plus y squared. R is in the interval from 0 to infinity, and we are gonna use a angular coordinate theta that goes from 0 to 2 pi, so that we can take from the x and y coordinates to the r and theta coordinates, and this is the usual polar transformation. So the other coordinates are x and y, and the new coordinates are r and theta. And you can invert this relation if you want to know what's the relation between x, y, and theta. You just divide y by x, and you're gonna find a tangent of theta, and you take the tangent or cotangent, and then you take arctangent in one of the sides, depending on how you exactly did this. And now we're gonna do the following. We want to change from a Cartesian picture to a polar picture. And to do that, we're gonna have to use the Jacobian. This is not the usual way you think about this. This is the mathematical way you think about this. But to link the Cartesian with the polar coordinate picture, we're gonna transform the infinitesimal element from Cartesian to polar. And when you do that, you go from a picture in which you integrate in strips, either horizontal or vertical, to a picture in which you integrate in theta first. So you have an element that looks like a sector of a circle crown, and you integrate in all angles of this crown, and after integrating all angles you have like a ring. And so you start with a small section of a ring, you integrate to the ring, and you integrate in the rings like an onion, as is very popular to explain this. As you can see, we explicitly make notice of what each side is, and to link the Cartesian with the polar infinitesimal elements, we use the Jacobian so that we can express everything in terms of the new coordinates. So the Jacobian is a matrix which we will take the determinant to know what must go beside the element in terms of the new coordinates. And to take the Jacobian, we take the derivative of the old coordinates to each old coordinates to each new coordinates, and then we take the determinant of this. So in the end we have that it is equal to r. Intuitively you could know that it is going to be r, because the infinitesimal element couldn't have to be r d theta. You can see in the drawing that's going to be it. When you vary theta here, this small arc here has to be r d theta, and the variation from r to rdr means that this must be dr. It's not always that it is this simple to see that this is the transformation, which is why we use the Jacobian. And with that, we can go from this integral to this integral. The x squared plus y squared is r squared. R goes from 0 to infinity, theta goes from 0 to 2 pi, and the dx dy becomes r dr d theta, and then we integrate in theta, which is going to give us a 2 pi factor. And after obtaining this 2 pi factor, we have this integral that can be solved via this variable transformation. Everything's here except the 2, so we put 2 above and below a fraction so that we get this integral 2 pi times the integral from minus infinity to 0 of an exponential divided by 2, an exponential in s ds. This gives us a 2 pi divided by 2, which is pi. Exponential of s from 0 to minus infinity is going to be 1, so this gives us pi simply. Focus, okay. So that I squared is equal pi, which means that I is equal to the square root of pi. This is the most usual method you find basically everywhere. And that is it. This is very important, as I commented before, in statistics and physics. So I guess this is a bye for now.